did our project, and I pre-wrote some stuff, because the one feedback was that I wrote small last time. But our project is basically on, very similar to what we presented as our paper, a theory of learning with autoregressive chain of thought, but this time we want to include mixed data. So if you remember last time, the motivation was like, we can consider a different function class, and then we want to see how much samples it requires to learn this function class, and so on. So we can review what we did last time, and it's basically this diagram over here. You take a sequence, and you take a function, you apply it, and you output a token, and you take the same thing, you apply the same function, you'll output a new token, and so on. And you'll iteratively do this t times until you get to this step here, and then this will be the token that we actually want, which we'll call our end-to-end function. So our class, our base class will be from functions from sigma star to sigma, and then our end-to-end class are all these functions here, the blue ones, that are still going to be from sigma star to sigma. And then in our previous presentation, what we really wanted was to see how many samples do you need to learn specifically this class when you have two different data. And then one data we had was we just had the input data and then the answer. And it looked exactly like this. You just had the xi and the yi labels and so on. And then the other data we had was we had also these intermediate steps, the z1, zt, and so on. So you think of it like you're trying to learn a math problem and you give textbooks and they have all its work and stuff. That's kind of what this data is doing over here. And then both cases, or in all the cases, we're in the realizable setting. So there's like this perfectly labeled function that can perfectly do it with zero loss. And then our goal was to path learn this class evaluated with respect to 0-1 loss. So it's important that we're learning this class, but we just have two different data. That's like the only difference. And then in that presentation, we've seen that if we just use this data, it's going to be log 2 to the t. And I wrote it like this for a specific reason, but it's basically going to be t, because log 2 to the t is just t. So it'll be t scaled linearly with our VC dimension of our base class. But then if we use this here, we're actually going to do log t, and then we're actually going to go through the proofs of this for our project. But now the thing that we changed is, instead of just considering all of these samples over here, like this is pretty good, it's log t. Like what if we had mixed data between the two? So we had some of these samples and we had some of those samples there. So what that's gonna look like is, and like the motivation is, you can train on some textbooks with showing all your work, but then you can also maybe have like Stack Overflow questions that just give you the answer. You're gonna have some of this data and some of that data. So the data that we're gonna work with, we're gonna call it data mix. And this will basically be some of this data, your end-to-end data. I'll just label like that because this is a little bit different than that. And some of data from chain of thought. And how do we actually define this? This is going to be, so we're going to have some of the end-to-end data like that. And we're still going to have m samples, but we're only going to have a percentage of that. So we'll call that, oh, I made the mistake, but we'll call that MP. So we're going to have p%. P is going to be a number between 0 to 1. And similarly, we'll have ym times p, and then we'll have some of the chain of thought data plus 1. And just assume that n times p is some kind of integer number. Like take the ceiling or floor. All the way up to m samples. So this will basically be the data that we're considering. And the one thing I forgot to mention was that in our algorithm specifically, because we eventually want to learn a function, we want to approximate this class using the ERM algorithm. And what that does is it just verifies whether the input and outputs are the same. So we have the algorithm for the end-to-end, which just verifies whether this and that is the same from our data. And then chain of thought was a little bit stronger because it verified whether this is true. And then our algorithm here will basically be a union of these two depending on what samples we have. So it's pretty much simple. It kind of just combines the two cases together.
Intersection.
Oh, sorry, yeah, the intersection. Let me just make sure.
Is there a lower bound as well?
No.
There's a lower bound for the very first one, which is that if you didn't have any chain of thought data, you'd have to suffer the log 2 to the t. So we know we couldn't do better than that.
So these are results. And from the start, like this isn't great, but you can see that if p is 0, then we just get, yeah.
This looks weird.
Why?
If I fix p and I scale t, the term that dominates is the 2 to the t term.
Mm-hmm.
And then it becomes essentially the first bound up to a constant that depends on p.
Mm-hmm.
And that feels weird because let's say p is 0.5.
Mm-hmm.
If I throw away half of my data, which is the data that's lacking the chain of thought,
Mm-hmm.
and I only train on half of the data that has chain of thought,
Mm-hmm.
then I should be able to get the log t VC dimension bound.
The log t one? The middle?
Yeah, because I just threw away half of the data, so I'm basically using half of the data. Okay, sample complexity goes up by a factor of 2,
Mm-hmm.
but the previous result allows me to say that, well, I can learn with that many samples. I can use the algorithm that was developed for chain of thought to,
50%?
yeah, just throw away the data that's like the bad data, like that doesn't have the chain of thought extension. It's kind of half of the data that I'm throwing away.
Yeah, so you're saying it's just a constant.
Yeah.
And then p here would be 1/2, and then you still get log to the t in this case.
Yeah, and that feels wrong. Like okay, as an upper bound, surely this holds, but
Mm-hmm.
I think that the upper bound should be just the second term, basically.
How is it just the second term? Oh, I see what you mean, maybe.
Yeah, because the good algorithm throws away the bad data and then keeps the chain of thought data. How much of the data was capped? Well, 1 minus p portion of the data was capped. So it's actually should be log t VCF epsilon over p or something. 1 over epsilon, and then
Mhm.
like the p comes in. Like I'm a sample complexity scales with 1 over 1 minus p. Yeah, in your case. That
Yeah.
should be the sample complexity.
I think I agree. This is I mean, we'll see what happens. It's like just naively tweaking both their proofs, and then you get this kind of thing.
Yeah. It's a project, it's okay.
Yeah.
Let's see what happens.
I agree, this is a good point.
Yeah.
Like, if we look at the extremes for this one, as Siddharth was saying, like, when p is 1, you do get the other one, but then it's a great point that when p is only 1/2,
Yeah.
you should discard half of it, and then you would get the other one that scales with like
Yeah,
a
factor of
constant.
2.
But here you don't get. You end up with
Yeah.
like log 1/2
Yeah,
to the t.
it cannot be, like, the cost of this mixture cannot be this high, right?
Yeah, which is actually, it's a really good point you mentioned this, because it has put a loophole into my naive thinking that if I take the two extremes of a bound and they match correctly, then it's probably right. You know, there's like my like
Right,
street
right,
fighting
right.
method of checking that the bound made sense was I
Yeah.
just checked the two extremes,
Yeah.
then I got the desired result, and then I just naively was like, okay, that seems like the right thing,
Yeah.
and then I just completely moved on afterwards.
Yeah. Yeah.
And so this is actually a really great experience.
Okay, let's see.
Okay, but let's continue the story.
Yeah, let's
But
see how this works, and
I-
maybe on the fly we can figure out what to
Yeah,
fix the proof.
but I guess the point of the story is that this upper bound might be weak or loose.
Yeah.
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 Can you explain the half thing maybe on the board for the rest of us?
Oh, it's just like, imagine in that picture that half of the data was chain of thought and half was end-to-end data. Well then, surely if your number of samples was only half the size of the, like if, like M required some amount here, and if you only made M half of that, then this term would say that, well, how would it scale? It would say that epsilon then doubles or something like this, I guess.
The same
Which is
thing,
fine.
or you just say that, like, that gives you the critical sample size.
Yeah.
If you have clean chain of thought data, no, you double that,
Mm-hmm.
but half of the data is going to be crap, it's
Yeah.
going to be end-to-end. You throw that away, you still have the same amount as the critical amount
Mm-hmm.
of chain of thought data, so you apply the algorithm that was giving
Yeah,
you
yeah.
that bound, and you get the epsilon accuracy, so
Yeah,
that's,
yeah.
that's a clean explanation.
Yeah. But when you do it the other way, it's a little, like, when you say you only had half of it, well then M said you need to double that, so then, well, then you have to argue that the accuracy would scale as 1 over, the
It's just-
epsilon, yeah.
Same thing.
But yeah, your argument is also fine.
Yeah.
I mean, that
Yeah,
one
this
is way nicer.
Was this clear? Okay, explain again.
Yeah. So suppose like, okay, let's do the argument this way. I don't think I need a marker.
Okay.
But, so we know that if you wanted to learn with chain of thought data, we told you need some amount of data which scales as log t, right? And then suppose you ended up with this mixture of data, right? Where let's say this mixture of data has exactly that amount of chain of thought data and that same amount of end-to-end data. So it's only twice as large. So like, I'm only requesting twice as much data, maybe not that big of a deal. Well, then my algorithm could just discard this half of end-to-end data and just run the algorithm that used chain of thought data to begin with, and it would succeed. And the only extra overhead I needed was that I needed the total number of data to be twice as much as the chain of thought from before, which is just a constant more than before, right? So basically I can achieve the same desired accuracy here. With this case, if I'm told 50% is going to be end-to-end, 50% is chain of thought, my algorithm just discards all the end-to-end. I then just run the chain of thought algorithm, and all I need to ask from you is twice as much data. However, in R bound, that would mean something like if P, which is the percentage of data that needs to be from chain of thought, well, this is the percentage of data that's end-to-end, but here it'd be 1/2. So if we were to plug that in, the bound we end up with is like 1/2 times 2 to the t plus 1/2 times t, which is basically just log of 2 to the t, that's the dominating term. And we end up with the bound for this setting, which is much worse than the bound here. And so that's the complaint, is that in the case where even like half of your data is chain of thought, you basically should be, well, if any constant amount is chain of thought, you should be basically doing as well as this, because it's only a constant difference, but in our case, that's not true. So
what does that prove? That the bound is incorrect? Or?
that the bound is loose.
Yeah,
Because
it's
this
correct.
algorithm is already doing exactly that thing. It's matching exactly, like it's making sure that the predictor you output is correctly labeling all the chain of thought data, which is exactly what this did, with the extra requirement that it also labels these correctly, which only reduces your search space. You know, so like, it's already, like this part, the second part, which I guess we haven't explained, is already exactly this algorithm. And then we have this extra data that allows us to restrict the set of candidate or predictors to be even stronger, and then somehow we get a bound that's weaker than this one for these cases where some constant amount is chain of thought data. So this has to be loose in some regard.
Yeah,
Yeah.
and maybe a non-trivial question to ask that goes beyond the reasoning that we were saying
Mm-hmm.
is that like how like the correct bound should be such that it should show that the bad data, the end-to-end data, if we blow it up really, really large, then it does help you to some degree. Like there should be some scaling with that. But I suspect that the actual bond is going to be just that. Like, so no, that's like 1 over epsilon, the epsilon multiplied by minus 1 minus p, okay? So that's one term of the bond. And the other bond of the term, the other term of the bond would be 1 over epsilon times p, like 1 over epsilon times p, and then like whatever s is in the bond, and you need a minimum of the two.
Mm-hmm.
Which roughly scales as the sum. So it's like this is how the piece should appear,
Mm-hmm.
I think.
Well, I'm pretty convinced it shouldn't appear this way. Or this is a
Yeah. But like the refined question is how does it appear
Yeah.
then? Because
Yeah.
in my bound the p didn't
Definitely.
appear. I mean like it appeared in just a 1 minus p portion, but if the 1 minus p is getting really tiny,
Mm-hmm.
then that bond becomes vacuous.
Yes.
So now, or like it becomes worse. So there is the interesting regime of like, okay, how do I, like what's the balance between
Mm-hmm.
bad and good data?
Mm-hmm.
Or maybe instead of just linear dependence over p, something like, for example, p to the minus t and 1 minus p to the minus t, something like that.
I'm not sure.
When t gets large, then because t is super large, for example, the coefficient of to the t gets a smaller exponential. You know what I mean? Then that
I don't know why you say that. My reasoning for this is because you can run a similar reduction for the other case when you throw away the good data and you keep the bad data.
Mhm.
If you have a lot of bad data,
Mhm.
you effectively don't have good data. You can still get that bound,
Yeah.
right? So that's why I'm saying that like the minimum of the two bonds is surely a bond.
Yeah.
So I think that, and then it's interesting that the p is kind of outside. It's like it's manipulating the epsilons
Mhm.
in a way.
Mm-hmm.
And I think that that's the correct form of the bond, but like, okay. I think that the upper bond is clear, the lower bond is not clear for this. Because the upper bond is just like this reduction, throw away the other hierarchy.
Yeah. Mm-hmm.
Even for that, you have to work a little bit because it's probabilistic that you have, I don't know, that many data points, but
Mhm.
like, you call, I don't know, lower flash numbers or something.
Mm-hmm.
Yeah.
Okay.
Right.
Yeah.
Maybe for this algorithm, the bound might be tight because this algorithm is not allowing you to throw away the data, like you have to interpolate it.
I think that's a good question. My suspicion this algorithm is at least as good as the algorithm that throws away the data.
I mean, it
Because
could.
the algorithm that throws away the data is not constrained even further. It could choose any of the hypotheses, and the proof says that no matter how you choose, among the remaining hypotheses, you will enjoy that bond.
Mhm.
So that kind of shows that this algorithm is at least as good as the algorithm that throws away the data.
Yeah, this algorithm is definitely at least as good as the other two because it just, like, if you didn't have any of this data, it's exactly the previous one. If you had this one, it's the other one, and if
I
you
mean,
had as much data as
The
you
other
needed-
one like has a degree of freedom to choose among the remaining hypotheses, and what Diego needs to know is that the bond holds for any choice of the RM
Yes, that's right.
solution, right?
That's right.
And in particular, it holds for that choice.
Yeah.
So.
So this extra check in either direction just refines your set even further from the sets you get here. I don't know if we actually explain, like, you want to explain the algorithms maybe in a little more detail because I don't know if we talked through them.
Yeah.
Okay, yeah. So the algorithm will just basically choose any of these end-to-end functions that hold the same. So this one here will hold the same input, the same as output. I mean, like, imagine like you had some points. You just choose like all the functions that kind of just go through the same points. But here the points will just be like x1, xn, and then that will be your y point. So there could be many functions that go through this, but your ERM will just choose a function that goes through all the points, that matches all the points essentially.
I don't think that's right. I think those points are supposed to be y1, y2, y3. And the
I
x's
don't know
are the
what's on the
x-axis.
figure.
Oh, okay, yeah.
It's space area.
Yeah.
But it'll basically choose any function that just matches all the points.
Yeah.
The y's,
exactly.
the labels.
Yes.
Well, at the inputs. So it's like, there is both x and y.
And then this one's just basically the same thing, but it matches also all the intermediate data steps. That's why when learning this one, it takes significantly less samples because you have to match also all the intermediate steps too, not just the final step.
Yeah, and another thing that we should be very clear is for all of these, your goal is just to output an end-to-end function from this class. That's the hypothesis class you need to pack learn. The only thing that changes is your data in all the cases. And the algorithm is going to take advantage of this new data by not running, in all the cases, over ERM over this class, but it's going to run over a different hypothesis class. And it's going to solve a different learning problem, actually. So what I mean by that is in this one, it's solving the learning problem where you need to just predict the y's. And it's just searching over a class that does predict y's. It's end-to-end functions. In this problem, since we know that there was a single function that labeled everything correctly, right? That means that there exists at least one function that outputs, remember what chain of thought does, it outputs the full chain of thought strings. We know there's at least this one that outputs it correctly. So we can treat this as a new classification problem where the labels are length t strings. So we have a multi-label problem, like where there's t dimensions of labels you need to match. And we're going to solve that problem. So our label space is now like sigma to the t. And in, I don't know if we wrote it anywhere, but like the label space in this case is going to end up being this sigma, which is just going to be binary everywhere in our thing, to the t. So that's how many labels we have. And so this is what ERM is doing here. It's running ERM with the function class that uses chain of thought. So it's solving that multi-label problem. And that, of course, gets all of these labels correctly, but we're going to see that it's going to reduce the number of samples you need because it's going to be constrained by needing to match all these intermediate steps as well. And we'll see how that kind of looks. And then ours just does the mixture of the two, which is that for these data points, it makes sure that it outputs these correctly, because F star end-to-end would do that. Well, for these ones, we know there is an F star chain of thought that would do that correctly. And so this runs it over a new hypothesis class, ERM, that solves this kind of multi-level problem where now your inputs have like a secret token we add telling you what type of input it's going to be, whether it's going to be an input that produces this type of label or this type of label, or sorry, this full chain of thought label, and then you run ERM on this mixture class, which either outputs this type of label or this kind of label. And then the results are kind of the same story as you would imagine in these. Yeah.
How can you guarantee that the intersection is not empty?
Oh, because we're in the realizable setting. And in the realizable setting, we know at least one function generated this. In this case, there's at least this function that generated all these. And in this setting, there's going to be at least one function that generates both this and this, right? That function is going to be this end-to-end. So like we're outputting, notice in all these cases we output the end-to-end function such that the f that the end-to-end function is based on, when outputting these yi's, does it correctly, and when outputting these chain of thoughts, does that correctly as well. And so we know basically f star is in this set and f star is in this set. That's the answer to that question. And it's strongly dependent on the fact that we have realizability.
And
right?
Just to be clear, the end-to-end only outputs this, but the chain of thought function will output your whole sequence of your intermediate steps and your final answer. So then that's how you compare it for this algorithm and that.
Yeah.
Sorry, so As you said, for chain of thought, we have T length of Z, which doesn't exist for N to N.
Mm-hmm.
And in a mixture, so we have the same length of input for both N to N and chain of thought. Is that the case? And
The X's are always the same. Yeah,
the
they're-
access are always
So
the
the
same.
domain's always the same, and the label space is changing.
So a question for the N to N, where does that T coming from if there's no middle steps?
It comes from the fact that the class we're considering that we need to learn is the end-to-end class,
Yes.
but I'm providing you a result with the VC dimension of the base class. If you didn't want this, the obvious result here that always holds is this 1 over epsilon, and instead of all this stuff here, this stuff here is actually just a upper bound on the VC dimension of the end-to-end class. So this quantity is less than this quantity.
Okay.
So we're gonna see this, the fundamental theorem, we're gonna see, which tells us that the number of data you need to learn any problem is just going to be its VC dimension of the class. So this is immediate, this is just like, this is how much data you need, and then the whole trickery was how do you relate this class's VC dimension to the VC dimension of the base class. And you could apply the same algorithm everywhere, and for all these results you would get the same thing, which is log 2 to the t, log 2 to the t. The whole like novelty is the fact that you don't run the same algorithm here and here. Here you run a different algorithm, which is the one that actually makes sure all these labels are correct. And then here, you're no longer, well, and then you're not going to talk about the VC dimension of this class anymore, because that's not interesting. We're actually going to talk about the VC dimension of
Chain of thought.
kind of this chain of thought class. And yeah. And so notice how solving this problem, where you get all these labels correct, you can immediately get a predictor that predicts the last thing correctly. Yeah.
So when they prove the lower bound, do they prove the lower bound for any f?
They show a particular f, which is like linear thresholds for which it holds.
Okay. So we don't like, and do we know that there are f's for which the VC dimension of the end-to-end chain of thought is potentially lower?
Yes, actually much lower. It can be 1, and the VC of f can be infinite, I think, or something like that.
Yeah,
They show an example of this too.
right, because things can collapse after t steps.
Yeah,
somehow.
basically like all of your functions can become the same thing.
Right, yeah.
Like,
Mhm.
in
That's
other
what I
words,
was
if you
thinking.
iterate, like all that the end-to-end function is just saying iterate your function over and over and over again. And
Yeah.
you can think of all sorts of functions that
After iteration.
after iteration, they all become the uniform or the constant function or something like this.
Yeah.
If you take like the identity 2 steps and then the not function 2 steps, they're the same thing. Because the not function, like
Yeah.
not
So-
and not is just the identity.
Nothing but not.
Yeah. So
Okay.
like your function of your end-to-end can be a smaller class than your base class.
Yeah, it can collapse.
What was the base class that we were collapsing here?
Oh, I think you were saying like you have two functions
and then
maybe.
not, or-
You just have like a constant function and like the not function. That's your base class.
Yeah.
And then after you iterate them twice, so when t is 2, you end up with a single function, which is just a constant, let's say, or something.
I see.
Or maybe the identity, sorry, yeah, the identity and the not. And here we're not appending anything, we're just
Right, right.
iterating,
Yeah.
composing them.
Okay.
But the point is there's like all sorts of function, like you can,
Funky things are happening.
with, at least with these finite classes, you can very easily come up with it. With the infinite classes, it turns out you can also do so.
Right.
Yeah. But
I
in
was
general,
also
you
thinking about how hard it could be to prove the lower bound for this chain of thought case. The
there's no
long-term.
lower bound here.
Yeah, but like prove it.
Yeah,
That's an opportunity to
I
do
agree.
something.
Yeah, definitely.
Yeah,
It would be interesting if you need the log t.
yeah.
Yes. But I don't have any.
What function class would do that? Well, yeah, I would try the function class that saturates the other bound.
Yeah. Mhm. No, I mean, there's all sorts of
Yeah.
great questions to ask here.
Okay.
And this was the running out of time, simplest thing. I didn't know what to do, which was just take these 2 proofs and combine it and then this, and I was like, okay, that's
Can be done.
one evening. Okay.
You have PM.
Hmm?
11 p.m.
Yeah, 11. This is Gemini, actually.
No way.
No. Once you see the proof, you'll be like, okay, that was too simple for even the left. No. Okay. Yeah, it's a good thing no one's presenting after us, eh? Because we were technically supposed to be done right now.
Oh, yeah. Well, in a way you're done, but,
Well, this is it. We were hoping to go through all the proofs, but
yeah, you can.
shall
We
we
still
do
have a
that?
lot of time.
Okay. Okay, so how's the rest of the presentation gonna proceed? Our goal is to prove the three things. We're gonna do them in this order. This one, because it's gonna be literally the simplest, is just really, yeah, it's gonna be quite simple. It's gonna be relating this to this. Like, and that's all you
Let's
need
go
to
for
do.
it.
This one, we're gonna do things a little bit more cleverly. And then this one's just like taking the mixture of the two proofs.
That one's probably the simplest.
And, well, once you know those two, then this is straightforward, okay. And then, the way we're gonna do that is I'm gonna need to present to you a theorem that tells you how much data do you need to learn some class, right? And we're not gonna define pack learning again and everything. All you need to remember is that you just wanna output some function based on your data that, labels things correctly most of the time, Okay. And so I need to provide you that theorem, and that's called like the fundamental theorem. And it's going to tell you that the number of data you need is going to scale with like the VC dimension of your function class. So if you are competing with more functions, you need more data. If you're competing with less, you need less. And in particular, the more and less is determined by this complexity measure called the VC dimension. It's somehow going to tell you how complex is your class to learn. And to introduce that, I'm going to do the terms in linear order, which is what I mean is I'm going to define some definitions, I'm going to state some definitions, which is basically I'm going to introduce the VC dimension, and then I will state the fundamental theorem, right? So I'm just stating these things so that I can state the fundamental theorem, then we will start the proof. And that's how it's going to go. Okay, so first, so I just want to introduce the VC dimension. Okay, so let me define some terms. So if you have, so our functions are always going to be like, I don't want to overload notation and use f. So from now on, like these functions and stuff, when we talk about the general results here, I'm going to use h for predictors or functions, right? And so if you have some sort of, so we're going to have, h is going to be our predictor from some domain x to some label space y. We're going to talk about data sets that are only over the domains. And so we're going to have like x1 up to xm, which are an element of the domain with m data points. And we're going to have a function class, which you should think of as like the base class, or the end-to-end class, or the chain of thought class, whichever one. And they're going to be subsets of your label space, maps from your domain to the labels, right? So some subset of them. So those are all examples of such things where like the base class was, this was sigma star and this was sigma. And for the remainder of the talk, sigma is the binary. Like, I don't know if we put it anywhere, but for the whole talk, sigma is this. So we're only doing binary classification, and in particular, all of the vocabulary is just 0 1s. Okay. And now it's going to turn out to be useful to kind of study the number of behaviors or labelings on these data points to determine how much data we need actually, in terms of to pack learn things. That's going to be kind of the important quantity. And so I'm just going to define some notation. So when a function takes in a data set, so a bunch of x points, it's just going to element-wise apply it. So this means the string or the tuple of h applied to x1 up to h applied to xm. That should make sense. And then equivalently, you can do it for a function class. So this is kind of the behavior, I'm going to use the terminology, the behavior of this function on these m data points, right? So you would get a string of 1s and 0s, which tells you the labeling it would do on this data set. And if I were to change x, maybe I get a different behavior on the data set. And in particular, I can study how many different behaviors does a function class give me. So I can say, if my function class, I'm now going to pass in some data set, and this is going to be how many behaviors do I get on this data set using functions from this class. So it's just going to be the set of all behavior. So this is a behavior, right? H takes in the data set, and such that that H came from my original function class. Good? Okay. And so now I'm gonna wanna just study, well, this is for the number of behaviors on a particular data set. I might wanna know what is like the most possible behaviors I can get out of this function class if I were to pick the best case data set, in terms of best case to make the most possible behaviors possible. And that turns out to have a special name called the growth function in learning theory, because it's gonna be a very important quantity. So we call that the growth function. And that's usually labeled as gamma of your hypothesis class. And now we're going to ask the number of behaviors I can get using my function class, like the best case number I can get, the largest number, for a particular number of data points. So I'm going to put an m here. So this is for m, and this would just be equal to the number of behaviors, so that's the cardinality of that set, right? The number of behaviors on a data set. And then for the kind of like the best case data set. So it's going to be the max number of behaviors over all data sets such that they come from a domain of size m data points. Okay? So hopefully that makes some sense. Okay. And now, shall I take 2 minutes to just motivate this VC dimension thing? Because I'm gonna tell you what the VC dimension is, and then maybe I'll tell you why that's the quantity you probably want to care about. So the VC dimension is going to be the largest m. Okay, well before I do that, how many behaviors can I get out of some data set of size m? Right. Well, this number can only ever be 0, 1, and this number can only be 0. And there's m numbers, and they can all only be 0, 1. So this is always upper bounded, right? By 2, because that's the number of choices for each one, 2 to the m.
Or y to the m, maybe here.
That's right. So if things are finite, it's technically y to the m. But in all of our things, y from now, well, okay, fine.
Let's just write 2 to the m.
2 to the m. I don't want it. So treat y as 0, 1, and x is 0, 1 to the m. No. Okay, so that's the total number of behaviors you can expect to get. And the question is going to be, well, you know, at some point I'm going to run out of functions to do this kind of stuff, maybe. And is there a point at which this kind of happens? And so, okay, the VC dimension, maybe I'll just write it and then we'll talk about why it's important. So there's a VC dimension, which we will call just the VC of a function class. And I'm just trying to find the largest m for which the number of behaviors is indeed all possible behaviors. So it's going to be the, okay, I'll write max first. The largest m. Actually,
D.
I don't like this.
Largest m.
It's going to be the largest number, d, right? That's a natural number, such that this quantity here,
The
yeah,
gross function.
maybe I'll use dots here, such that this
Go
quantity,
on.
oh, not this quantity, the growth function, for that d is equal to 2 to the d. Right? I don't know why that was so complicated to write down. Is the largest number such that that growth function is indeed equal to 2 to the d. Yeah? Okay. And that might seem very arbitrary why this is the number I care about. Why do I care about the number of behaviors? And this point where it cuts off and no longer can display all possible behaviors seems to be the point that is of interest to me. I'll give you 2 reasons. One is because of the following theorem. So I'm going to call this the fundamental theorem of learning. And then it's for binary classification, and then we're going to actually, so fundamental theorem of learning. And the statement is like this, which is that ERM, which we're not going to get into the details of defining the thing, but what is ERM, right? The ERM is you just take an estimate of your loss. You have the 0, 1 loss, you have your data set, you take a sample mean estimate of the loss. So you calculate the loss in every single data point. You take the average, the empirical average, and that's called your empirical risk, and you try to make that as small as possible. You minimize that. And since there is indeed one function that perfectly labeled everything, at least this function will get 0 empirical risk. It'll label everything perfectly. And so that was also why this was called empirical risk, and it's equivalent to this. Empirical risk, minimizing your empirical error, your empirical loss, is the same as just picking any function that labels things correctly. Anyways, if you do this empirical risk thing on a hypothesis class, H, or a function class H, well then, the fundamental theorem says that this learner, right, is going to pack learn that corresponding function class with how much data? Well, the amount of data M is going to be big O of 1 over epsilon, it's the wrong epsilon, 1 over epsilon times the VC dimension of the function class. And it also says that, and I'm not going to write this, but the reason it's called like the fundamental theorem is it says that if you had an algorithm, if you came to me with an algorithm that you said pack learns in H, right? And you told me your M is lower than this rate, so maybe you had, I don't know, log of the VC dimension. Well, I will tell you I can always find a hypothesis class which that's not true for you. So it's not possible. In other words, this is the best kind of number of samples you can get. And in the realizable case, this is indeed 1 over epsilon. Okay, so now maybe I'll say like 1 or 2 minutes about why this is maybe sort of the right quantity and this behavior stuff is good. Because we're going to talk a lot about behaviors for the proof. And roughly speaking, okay, this is going to be the plot you should have in mind. So you have like your domain X, right? And so, okay, just zoom out, forget about all this business stuff. And now I'm going to tell you about what is called like the no free lunch theorem, which is going to tell you that, so like the question is, forget about your hypothesis classes and so on. Like let's say you just, somehow there's like data being generated somewhere and there's some function labeling your data. You have no idea what it is, and you want to learn what it is. But it can be any possible function. You haven't restricted yourself at all. Well then let's say there's, for simplicity, let's say there's 6 domain points. And so you get a data set, right? And you see like this point, and you see this point, and you see this point, and this is like 0, 1, right? So these are the labels you see in your data set. And now you need to tell me what is the function that labeled my data, but you have not seen any data points here, right? And so you haven't seen these points, and unsurprisingly, if you want to get more than something like, let's say, half of you, if you want to predict more than half of the points correctly, you're going to need to see how many data points? Well, at least half of the domain, right? Something like this. Or in other words, you're going to have to see, to get some accuracy that's like size of domain 1 over size, whatever accuracy you want, you're going to need to see at least that proportion of data points. So if you want to see, like, if you want to get 5 out of 6 accuracy, you're going to need to see 5 out of 6 domain points to get that accuracy or something like this. And what did this whole like claim hinge on? Well, it hinged on the fact that the true labeling function could have been anything on these points, right? Because I need to pick a function. I need to pick some sort of behavior over here. And what I mean is, like, if I get evaluated on new data points, which could come anywhere, because let's say your data points are coming uniformly, well then, maybe I pick this one. Maybe I say on these points, I'm going to label them like this, because I really don't know better. Well then guess what? My adversary, or in other words, the true labeling function, could have been something different. The true labeling function could have actually been like this. And in particular, it could always be the complete opposite of what I do. Okay, so that turns out to be a really big problem. And the way to solve this problem is to not let the adversary have all possible power on all possible points I've never seen. Okay, and so how am I going to fix that problem? I'm going to say let's restrict the hypothesis class. Let's restrict the set of functions I'm competing with. And then the question is, at what point does this problem get overcome? Or in other words, at what point does my adversary not have all possible behaviors on unseen points? And it turns out that that's exactly like the VC dimension. That's the point at which the total number of behaviors that my adversary can pick from, or that the unknown function came from, is not all possible behaviors, so I don't run into this issue anymore. And actually it turns out that it's kind of dramatic. The moment you pass that boundary is exactly the point at which you can actually kind of successfully learn. Or your prior knowledge from your hypothesis class kicks in that you no longer need to compete with all possible behaviors. Okay. That was only 4 minutes. Good. So that's why that's kind of the right quantity. Hopefully it makes complete sense that at that point you no longer run into this issue. The fact that dramatically after that point, afterwards everything is good, is maybe less clear, and that requires more proof. Okay, so we have this thing, and yeah, the final thing that I really should tell you about is that, okay, when you work with binary labels, all is good, and we talk about this VC dimension of this stuff. But when you work with non-binary labels, which we're going to work with here, for instance, right, the label thing was complicated. It was sigma to the t here, which was not just 0 or 1. You needed to label, you needed to output something in here for your labels now. So what's going on? I can't do the VC dimension anymore of that function class, because that function class, chain of thought, is outputting t labels, right? T length things. So there's two alternatives. One is that you use the equivalent kind of statement for multi-class classification. And we're not going to do that, because actually if we do that version, we're going to run, for this special structured version here, we're going to run into getting the same bound as this here. And so what one notices when you actually work through these proofs is that the thing you actually need to control is not the number of behaviors that your function has, but the number of behaviors that the loss function can have, basically. Because remember, for each function, it goes through a loss, and then you want to know how many different ways can the loss change. Okay, so we're actually going to be talking about the behaviors of loss classes. And when you have 0, 1 loss, you can already see how this is really wonderful, because 0, 1 loss, what does it output? It outputs 0, 1. And so you can think of a loss as itself a predictor to 0, 1, and you can talk about the VC dimension of the loss, and if you do that, you get an equivalent fundamental theorem with for loss classes. And then all I wanted to do was define the loss class. Where is the definition? So I'm going to replace this with something like not the VC dimension of S, H, but the VC dimension of the loss class of H. It's going to be a number of behaviors of a loss. And so the loss of y hat y for a particular function, for a particular H, is just the indicator that H of x and y, like a data point, is just whether you got that wrong. This is 0, 1 loss. And so the loss class, when I write L of H, this is the set of all functions that take x to x, y. So we're going to think of this kind of as a z. This is like a z point. Kind of like before when you're thinking of these type of functions from x to y. Now we're going to be thinking of functions from, the domain. Maybe I should write it as this is an element of cross y. Y here is going to be anything, actually. And what does this map to? And I'm writing, this is like this kind of, the functions are maps from x, y to exactly this L of H type of thing, L of H of x, y, such that H comes from the hypothesis class. So basically, take every hypothesis or function in your function class, get an equivalent loss function from it, right? Just plug in the H there, and now treat this as a function of x, y as your domain, and the range is now going to be this thing here. It's an element of 0, 1. And so you can see that this looks just like a binary labeling function. And because of that, we can talk about its VC dimension. And it turns out that this quantity is the correct one to talk about the number of samples you need. In the binary, when this is indeed, when y is 0, 1, these are the same. And for anything larger, this can be potentially smaller, because you can have less behaviors over losses, but still a lot of underlying behaviors over functions, and we're gonna make use of that. Okay, so at this point, maybe we can do the proof.
Yeah. Shoot, because you will run out of time.
Yeah, maybe that took too long,
Okay.
as
Sorry.
usual. And I'll introduce, well, you can introduce Sauer's lemma along the way.
Okay, so the proof is kind of simple. Like we want to relate this class with that class, and what Vlad just talked about, this class is basically the loss class. We want to relate this loss class with that class, ideally just bound it, and we're going to do that using the growth functions. And then with the growth functions, we can use something called Sauer's lemma, but to relate the growth functions, we probably want to do something in. So what I'm going to do right now is I'm going to extend the data that relates the base class with the end-to-end class. So I'm going to make something called data end-to-end extend, which is now going to be all x and these intermediate chains such that x comes from the end-to-end data, and z is some length of t for all t, like that. And like the picture of extending the data is, imagine you have some kind of vector here, like x, and since we're in the binary case, it's either going to output 0 or 1. So what it can do is, the next step could either be, let's call this z1 is equal to 0, and z1 is equal to 1, and so on. And then this basically takes all the data like this, it takes all these chains here. And the reason why you want to do this is because the end-to-end data has all the x vectors and the y vector, but in order to relate to the base class, like for example, to get to the y step, you want to take this length, input into the function, and then output the answer. So that is why we extend the data like that. And what we can ask is, what's the cardinality of this extension? And in doing so, this here is basically going to be cardinality of the end-to-end times this tree of different possibilities 2 to the t, like that. Okay? And then this here can just be upper bounded. There's m samples here, and then this is just upper bounded by 2 to the t. So hopefully that makes sense. And the reason why I introduced the extension class is to relate it to the growth functions, and the growth functions will relate to the VC dimension, and that's kind of how you prove it using the fundamental theorem of learning. So I have this claim here, and this kind of relates the two classes together. And the claim is that if the loss on the end-to-end for some functions, maybe say g and f, they don't equal to each other, then this implies that there is some kind of chain, there exists some kind of x z to the t chain such that f of the data from the end to end, I may have got the, okay, extend, I'll just erase this. Doesn't equal to this. Okay, so what this is saying is that if the loss function, if they don't correspond, then their base function doesn't correspond either. And you can kind of think of it like if these two here, well, let's think it here, if there's two functions that don't correspond to the same y value, then if you take the base function from x to z, then these won't correspond to the same y value either. So that's what you do over here. Okay, so then with this claim,
I guess basically like if the final output is different, which is the only way your losses are different, right? Then that must mean that there existed some extent, some like path along the way on which the base class, when it was applied on, differed, right? And that could have been like at any of the t steps. And the data, like, it could have been like, and you consider every possible like chain of thought that could have happened along the way, and like clearly on one of those you must have been differed if your loss was different at the end. I don't know.
okay, hopefully that kind of makes sense here. And then what we can do is now, this kind of corresponds to the different behaviors we can have. So the growth function now of our loss class. How can you write it?
F and 10.
Okay. This, with respect to our end-to-end data,
Okay. This extension, it kind of, you drop the labels, the Y's. Like in D, E to E, you had the Y1, YM. Are those gone, or like you're appending them to the end, or like?
No, they're gone because
gone?
we're going to be talking about the number of behaviors the base class has on it. So we only want to talk about the X's. So like in here, right, we talk about these type of data sets.
But then when we made this claim, shouldn't we worry about that you drop the Y's?
No,
Because in the claim, you say that like, oh, if like I have two F and G different, and then some other losses are different, then there has to be some step where they are different.
yes.
But like if it's the last step, like you drop the last step, that's where they were
Well,
different.
no, so we've dropped everything up to this step, and we said that if your outputs, so if your losses are different, then it must mean that your functions outputs, like final outputs, must have been different, right? That's the only way your losses could be, your end-to-end outputs, which
I
means
I just don't understand the formalism that's on the board, because the Y's are given, or the Y's are dropped from dx e to e.
yes,
I don't see any Y there.
that's right. There's no
But
Y here.
maybe when LG is not the same as LF, then it's because of the Y's.
But that's not so.
No?
If they're not the same because of the Y's, then that must mean, right? That what do they look like? They're end-to-end functions.
Okay.
And what does the end-to-end function do on the step right before the end? Well, it will apply the base function on some prefix of this length, right? And therefore, if the Y's were different, then that must mean the base function applied on some input up to length t minus 1 was also different. And so if the base class and so we've considered every possible chain of thought up to this length, up to t minus 1. And so basically, in other words, like if your end-to-end function behaved differently here, then what that means is that your base function for inputs up to there
Right.
must have been different on some input. And we
Yeah.
consider every possible input.
Yeah.
And if it wasn't there, then maybe it was before that. And if it
Okay.
wasn't before, it was before that. And it's like really kind of, you might think overkill to consider every possible
Yeah.
reasoning
Yeah.
chain up to there, but it'll definitely be sufficient, right?
and then for this case, they do have the lower bound, which is the same.
Yeah.
So technically, it wasn't overkill doing this extension.
Mm.
So we can consider the number of behaviors, and because of this claim here, since this implies that the number of behaviors on the loss class with the end-to-end data is less than or equal to the number of behaviors on the base class with the extended data. I should have wrote this here. But that's basically, this here, we'll get to this inequality there. And then, because the cardinality of the extended data is less than or equal to this over here, this is less than or equal to the growth function of m to 2 to the t. So now it would be good to introduce something called Sauer's lemma.
I think you should say one more thing. Or this maybe I could say. So like, I still feel like we don't know where we're going with this proof maybe. But like the whole goal is to find what is the VC dimension, the beta bound on this VC dimension, right? Well, really the VC dimension of, like, we want to bound this thing. And then I'll introduce Sauer's lemma in a second. But we want to bound this thing. Right? How are we getting there? Well, if we remember, what is the definition of this? It's the largest m for which the growth function of this loss class is going to be the same as 2 to the m, right? And so, in particular, if I were to find any m such that it is this quantity here, 2 to the m, is strictly greater than this, I'll be done, right? Because I know that, so in other words, the VC dimension is the smallest m for which this quantity equals this. If I find any m for which this quantity is strictly larger, I'm done, right? And so I just want to solve this equation, which is this strictly bounded by this. What is the m? That's my goal. But what I'm going to do along the way is I'm going to upper bound this by a few things. In particular, I'm going to upper bound it with things that depend on the original base class. And then once I get a formula for this, I will then relate this to this. And of course, if I get a strict upper bound of 2 to the m on this, then I'll have a strict upper bound on the original thing and I'll be done. Okay, so all that's left is, do we know, like, what does the growth function look like of something, right? This is what the next lemma is going to tell us. We're going to get like an upper bound on this quantity. And so Sauer's lemma, I guess I read here. So there's this thing called Sauer's lemma. It gives us an upper bound on the growth function. And we're going to specifically study the case where, in the case if m is greater than, I'll use a different variable. If d is greater than or equal to the VC dimension of some function class h, then Sauer's lemma tells me that the growth function of that function class h for any d, right, any d greater than this, what is it? Well, it's going to be less than or equal to e, the number, d, okay, that's it.
Maybe you should have used m, if m is not bigger than VC dimension.
I don't want to use m because there the m is going to map to m, and I don't want to
Right,
be
right,
confused.
right. But the d is like usually the dimension, and
Yeah.
so it's like
Okay, here.
really k. Yeah.
Okay, we'll see why I didn't want to use m in a second.
There we go, saved.
So VC of h, VC of h, yeah. So in other words, k can keep going greater than VC dimension, so VC dimension of 10. However, the number of behaviors is just a polynomial function with a polynomial power of 10. So it doesn't exponentially grow with k, right? They'll, like, we obviously knew this. This was obvious. This was just the definition. You know, it couldn't be more than that. That was that m over there. However, this is something much stronger. It says that after the VC dimension, it's a polynomial growth now. And that's beautiful. And that's somehow characterizing this fact that I was saying, that after the VC dimension, the number of behaviors no longer grows exponentially. It's exactly the cutoff point at which things start to grow polynomially. And that's what's going to be plugged in there now. So you can put that there.
Okay, so then, you're just using Sauer's lemma. We can just bound this, assuming that m is large enough where it's greater than the VC dimension of the base class. It's going to be,
Is it m squared 2 to the t is bigger now?
Yeah, maybe I can plug that in at the same time. This is under the constraint that m, 2 to the t, which is like the k from before, is greater than the VC of f. So after this point, that's true.
so now we just have to find some m that this holds. And obviously if M is like really, really large, this is gonna hold, but like what's like an upper bound on M that we can find? So this holds, and ideally, the upper bound gets us to this result over there.
So there's a lemma
Yeah.
that says that if you do some math to try to solve this problem, which is find an M such that this quantity, this 2 to the M is strictly greater than this, and this constraint is satisfied, you can find one, and the corresponding M that satisfies such a thing is any M, you can find an M that's not too big. That's the whole goal. I don't think we even need to put those things. Maybe you just get the final result.
Okay.
There's a, forget about this. Maybe should I put okay, maybe we should put the lemma. Oh, yeah. Okay, so you pick any N, you pick any M, and then you say, you can show that there exists an M such that the following holds, which is N less than or equal to M less than or equal to, this is the important thing,
Should there be a 2 to the t in the brackets?
I see.
If
Yeah, there's a 2 to the t missing. Anyways, there's a lemma that basically says that you can find such an M.
And just to finish off, you just let,
And the M's not too big.
so when you let N equal to the,
What optimization are we showing?
Once again, I want to find an M, right? I want to find an upper bound on little m, such that this strict inequality holds, and it also satisfies this constraint.
Right. So since exponential growth is bigger than the polynomial growth,
Mm-hmm.
I have to start with some small m. If m is really small, then probably this holds for a while, and eventually the exponential growth overtakes the polynomial growth.
Exactly.
Left-hand side polynomial, right? Like right
So
hand
yeah,
side
eventually, and then the
exponential.
question is, can I get an upper bound when it's not too large, at which it takes over?
So there is a crossover. Okay, you're taking the log and then solving the equation.
That's right.
Mm-hmm.
And it takes a few steps.
Yeah.
But the point is, yeah, you just want to
Like-
find at what point does this take over, and is that point not too late, or not too long, or it's not too big of an m, at which that takes over. And if you solve for it, it turns out that if m is smaller than this quantity, well, then this is true. If the exponential growth takes over for an m small, but like, there's an extra constraint, right, which is,
It should be bigger than something.
it also needs to be bigger than, and the bigger thing is this, actually. And also that, yeah, as long as m, yeah.
and then if you just go through the steps, this will be log t, something to the power of t. So then it'll just be t times log your BC dimension. And then that's how you get this result over here. I just want to go.
This was 2.
Yeah.
Change it to 2.
Okay, it's because we're in the binary classification.
And so that's where the log 2 comes from. And this, yeah,
Yeah, and then you just go through the steps.
Mm-hmm.
Some kind of constant,
mm-hmm.
t times.
I don't think there's the VCs cancel, yeah.
Yeah.
So that's not in there. Okay, anyways, you get the result.
Like that.
Gotcha.
Okay. The chain of thought proof is the same thing, except you just change one little thing basically. Is you now study the, okay, so what's happening in the chain of thought case? In the chain of thought case, you want to ask, what is the number of behaviors, okay, of not the end-to-end class, but it's going to be the chain of thought class. So this is going to be the class. Okay, there's this class, F chain of thought, which is now the chain of thought functions. And the important thing is this is a subset of functions that map from sigma star, not to sigma, not to 0, 1, but to sigma t. Right, so we have this multi-label thing. Okay, so now we're just solving the classification problem with labels of this form. Okay, great. So I'm just going to replace end to end here with chain of thought. And my data set is the chain of thought. So okay, so we got, so far we got this bound just now. All I want to do is show you how you're going to get this bound now. And the way that's, yeah, so you replace this. Now we're going to control ERM that's working on the chain of thought type of classification problem. And recall that if you solve this multi-label thing, you've of course solved the original problem because you could just take the final label of your predictor that already outputs these chain of thought things. Okay, so let's solve that new problem. And yeah, so this is the thing we're going to want to bound now. And the question is, can we do better than bounding it by considering all possible extensions? And the answer is going to be yes. And how do we think about this? Well, we think about it like this. Like, okay, what is the number of behaviors on this loss class? Right? Okay, well, we do the same study, which is that, like, let's take a function g and a function f, but now these functions g and f come from a chain of thought class. Okay, and now the question is, how could their losses have differed? Because that's the only way a behavior differs, right? If the losses change. Okay, so how could this be the case? I just need to say, like, basically, like, if this is true, what does that imply? Okay, well, that implies that there must exist some x and some chain in the middle, right? On which the base class was not, like, the base classes differed. However, I don't need to consider any possible extension now. I only need to consider the actual extension that they were tested on. Right? So on each data point in, so these are chain of thought now. Oh, this is good to see the changes. The chain of thought, oh, maybe red is. And so, once again, how did these possibly differ? There's F or G. Like, how could their losses have differed? Well, their losses would have differed, once again, if they outputted a T-length sequence that was different than the other T-length sequence, right? These F and Gs, they output sequences of length T, and the losses compare, are these T-length sequences exactly equal to each other? This is what the multi-label loss does in this case. Okay, and the only way that that sequence would not match, or if the sequence doesn't match of these two f and g functions, well, how could that be the case? Well, that could be the case if, right, how are they outputting sequences? The way they're outputting sequences, they're applying the base class t times, and it always has to be applied on, like, on these things. And so, yeah, basically it must be wrong on one of these prefixes, but the prefixes are no longer any possible sigma t, but
they're f and g dependent.
yes, the z now f and g's on one of the prefixes was different. And so this extension thing is now prefix, and before these should have been f and g end to end, and this was f and g base class. And this is prefix. So anyways, everything's prefix. This is now prefixes, which are prefixes based on the specific z's you actually saw. And so once, yeah, like the claim really says that, like, if the losses were different, then it implies that at least at one of the time steps, you outputted something different with your base functions, which is this one. And now because of this, you count, well, how many things are here? Well, the number of things here is number of data points. That's the size of this. And then how many ways can you take prefixes of t-length things? Well, there's t ways. So instead of that whole thing, you now just end up with m times t. And then everything's the same. This is now prefixes. This is now not m2 to the t, but mt. This gets replaced not 2 to the t, but mt. And this final bound has not 2 to the t, but t. Okay. And it should make complete sense, right? Like, if you had this extra data, what has now happened is you've restricted the set of possible, like, functions that label these y's correctly. So, like, in this case, right, there was f star obviously labeled things correctly, but then there might have been a whole bunch of other functions that also label these points correctly on the data set, However, if you were to get new data points, they don't maybe get it correct, but in particular, the in-between sequences could have been different from F stars. But now we've constrained it further. We said that, oh, not only do we ask you to get this thing right, but also every in-between sequence we ask you. So in some sense, it's like, yeah, it really reduces this exponential possible behaviors in between that you could have got wrong, to now constraining it that you got to get these right. Okay. And so then the way this proof works is it essentially combines both of them and realizes that if you have these two data sets, then on the part of the data set that is the end-to-end one, then the losses can differ based on this, and the other one it can differ in this chain of thought way. And then you end up with here having the growth function of something like this data set plus the end-to-end. And you end up here with this prefix and then the extension version. So it's like chain of thought, and then here you have extensions, end-to-end. And then you end up essentially having this plus M bound thing, and then that's how that goes. Right. So it's a very naive application of their proof, and that's how that would go through. Yeah.
The other thing is like, this is mixed data, but then you can also have partial Zs that are correct. You might not have the whole reason chain. So then like the question is, can we leverage these partial information? Because right now if you only had partial information, you would just throw off all the partial information and it would just be your bad data. And you should be able to leverage.
Right, you can have some intermediate.
Yeah, which actually just is like, you now end up with like kind of the, I mean, if we do the tree view, right, what was the difference? We had this X here,
Yeah.
and then there was some sort of reasoning choices that, like
So
some
let's
Z,
say,
and then some other Z's maybe,
yeah, you have T1.
and then you end up with the final Y. Maybe, and so this is your Y, this is where your Y is coming from. And in the case where you get nothing in the middle, you really have to consider all possible paths.
Yeah.
In the prefix version, you constrained yourself to a particular path for each data point, and then you had to just make sure you matched every step. And then if you get some in-between thing, then you prune the tree, at least like maybe make it to this step here, and then only consider the subtree.
Yeah. So imagine that you have T1 length prefix after X, and then T2 is missing,
Yes.
and then there is a label. That's one case. The other case is you want a T1 gap, and then T2 filled in, and then you have the label.
Yeah. I think that's still
Are
okay.
these two cases different in any ways? Or like this proof cannot distinguish between them, but
I don't think it will distinguish between. We thought
yeah,
about it for like 10
that's
minutes.
what I think. That
I don't
it
think it
doesn't-
will. And I think it could even be like, you get the first step, you miss the second one, you get the third step, you miss the fourth,
Right.
and it doesn't
But-
matter. Which is
But
kind of weird.
is it real? Is that a real effect, or is there a difference between these two? I don't know.
I don't know either. It
Yeah.
feels like if you knew the beginning steps, then it's somehow better than only knowing the final steps. Like if
But
there's
maybe having any gaps anywhere is like kind of equally bad.
yeah, I mean, I think this will say that they're the same for their
Right, right.
Which
And
is kind
maybe
of
in a
interesting.
worst case sense they are equally bad, but maybe there's some hypothesis spaces where
Mhm.
having the gaps at the beginning is worse than having the gaps at the end.
Yeah.
Maybe sometimes it's the other way around, who knows?
Yeah. And actually,
Those are interesting questions.
yeah, and actually, the whole project started. The only reason we did this was because it started from a different question,
Yeah.
which is that currently F star. There's only one F star that's generating things in this case, and in particular, like basically, you have the proofs for like. You have these intermediate steps that are always generated by the same F star,
Mhm.
which is to say that like you always have the same math author writing your proofs, and you never see like any different styles of writing proofs or any different strategies and so on.
Okay.
But like, you could imagine you have some data of like from some author.
Many
text-
different possibilities.
Yeah, many different likes, but all get to the right answer. Okay, this is what I'm trying to. There's a bunch of ways you can get to the same final answer, but intermediate chains are all equally valid, but they're different.
But maybe even the final answer can be written in different forms.
Well, let's
Yeah.
just think
So
about.
maybe this just goes back to loss classes. Because a loss class would be the big equalizer, because it asks like, but was it correct?
Yeah.
Was this step in the derivation correct? was this final answer
Yeah, yeah,
actually correct?
yeah.
It's not the label, but
Yeah, but the interesting thing is then the algorithms are tricky because, right, the way this, at least the consistency style algorithms are working is that we know that at least this f star will be in this class. But now for the...
just ask the semantic equivalence question. It's a special laws.
oh yeah, I guess what function makes that special law 0?
Yeah.
Maybe that's reasonable, yeah. The whole loss-based view came after the...
That kind of goes
discussion.
back to multi-class, and in a
Mhm,
multi-class
mhm.
case, it's kind of harder, the whole thing.
Yeah, that's fair. Anyways, this thing, the interesting, well, I don't know how you, but like, you get a corollary from this, which is that even in this like what I'll call multi-experts, like multiple correct reasoning things, that as long as you have one expert that's doing the right thing, some percentage of the time, you can just discard all the other ones, and then you end up with data of this form.
Sure, if you know which expert is producing what data.
Yeah, but even if you don't know, you can always just find the largest chunk for which you can get correct labels, right? Because the whole issue is that like you can't pick a single function that does all the steps correctly.
Right,
Like,
right.
and so then you can always narrow it down to a smaller chunk, and it'll always be so. As long as you can treat this
Right,
as you have
right,
this
right.
percentage of a single expert
Yeah.
labeling things.
Yeah.
So that kind of also holds for that. That's because that was the case I was first interested in, and then I thought that if I solve this problem, then at least with that condition I can get that claim.
So that feels like data contamination problem that you're solving there, because the other experts are injecting stuff which is somehow a distraction. You want to filter it.
Why is
So
it a
that's
distraction?
called data contamination.
But why is
You
it a
can-
distraction? It's like it's
Because
also
it's
valid.
like you want to reject them because you cannot represent them, right?
Well, like I can represent them. I can represent all of them. Let's say all of them are in my function class. The
No,
only
no, you
problem-
said that like some of the experts you cannot represent. I said
I
that
can't
was
represent
excused.
all of the reasoning chains with a single function in my function
Yeah.
class, but I can represent each of them individually with a function. Right? So like if I had to pick one function, I can't reproduce all of them.
Right.
But if for each data point I could pick a different function, then I could reproduce the reasoning. Right? So that's the difference. It's like if I had to stick with, there's no single function that labels all the reasoning steps correctly.
Right.
But there's different ones at
But
different.
it's more like the multi-label
Yeah.
setting.
Yeah.
Yeah, with that view now, I'm seeing that maybe that's sort of, which is what we got to, yeah.
Yeah.
Which is interesting. I mean, this whole realization of this, like, in the multi-class case, you then, maybe it's, like, when the label class gets more funky, thinking about the VC dimension of the loss class
Yeah.
is kind of nice. And that was a cute.
But this is more like multi-label, not even multi-class. There are many possible labels that are correct.
Oh, right.
Yeah.
Yeah.
Yeah, those were the only two extensions, the actual partial data and the mixed experts.
Maybe not even multi-label.
Well, I guess like the other thing is like this bound is loose, so
Yeah.
there's that thing too.
But that you can,
Sorry?
that, like the looseness you can fix, but,
Yeah.
okay. All right, good.